Welcome everybody to this SDXS Troubleshooting the Fabric session. My name is Michel Peters. I'm a technical leader with engineering. I'm part of the Enterprise Networking SDA solution team. For those who work with TAC, who that SDA, when TAC is saying they're reaching out to the BU, it's typically to me and my colleagues. We have a small team spread across the globe. So whenever TAC has an issue, they open a BEMS case and then they engage us. So that's where we typically are. We only have about 7 people in our team, so it's very small. So sometimes if they do escalate to us, it does take some time, but that's because we just have limited availability with the number of people we have. We're going to talk about SDXS, troubleshooting the fabric. I come from the Catalyst 9000 background, or the Catalyst switching background. I started with the 3500 XL, so I'm focused mostly on the device side of things, even with SDA, not the provisioning side that some of my other colleagues like Vaibhav, Rahul, and Yogesh that do that part of things, so you might have worked with them. I normally work with the devices itself. What we're going to show you today is mostly some things that we use a lot to be able to troubleshoot the things that we look at. Just to give you some understanding, if you have SDA deployed, what to look at on the device side, to see what might be going on, where to look at, how to see the forwarding, and just get some general idea about what's going on, especially if you have anything happening that you don't expect to happen. It might help you trying to understand it. Obviously, you can always open a TAC case. They will help you as well, but this will give you some understanding yourself. There's a WebEx Teams room created for this one that you can join via the Cisco WebEx app. We'll monitor it till the February 24. So if you have any questions during or after the session that we can't answer during the session, feel free to just post it there. We'll try to respond to it and try to give you an answer if we know about it, or we'll take it further just to see what's going on. We'll monitor it at least till February 24, but if you have any questions after that, I'll typically notice anyway, and we'll try to respond as well. So you can use it. You can join it via the Cisco WebEx app and ask questions there. You can also ask questions during the presentations, but sometimes that's a bit more complicated, or after the meeting, I'll be here as well to answer any questions. So the agenda for today, we'll just look at the basic fabric, what it is, just to make sure that we have a good understanding what the fabric is, what we're talking about. Then we'll look at endpoint registrations, your endpoints connecting to the fabric, how do you actually get into the fabric, how do you get registered. Reaching remote endpoints, that's also, of course, the purpose of your network. You don't want to just have an endpoint connected, but you also want to reach somewhere else. Traffic forwarding through the fabric, how that works. The secure fabric, so that's the CTS segmentation, the authentication that happens, and also the policing and the profiling that you have in the fabric. And at the end, we have some multicasting, some introduction into the multicast troubleshooting. Multicasting is quite complex. I'm just covering a smart part of it. There's also another session at Cisco Live about demystifying multicasting and SDXS. So if you're interested in multicasting, that's also something you might want to look up after Cisco Live, just to look at the recording. I think it's playing at the same time, so it's going to be difficult to visit well. But that should be a good session if you have any multicasting issues in your network and you want to get a better understanding of it as well. So just to look at the fabric, what it is, just a basic overview. You have an underlay network. We don't only do layer 3. That's because we use a lot of IP Anycast and MAC Anycast addresses. So we have to have an underlay with layer 3. If you start doing layer 2 and all the VLANs start merging together, it becomes one big mess. We tunnel everything anyway via VXLAN. So we have an underlay that's purely layer 3. It will stabilize your network as well and make it much easier to maintain itself. The important part for the fabric, which is mostly the brain of the fabric, is the control plane node. It can be 1, 2. I think we support up to 8 control plane nodes. That's a bit excessive, but at least it's always recommended to have at least 2 of them in case one of them crashes for whatever reason, that you have a backup. Some people also run it on a SVL pair. Then you have virtual redundancy inside the stack. But sometimes it's just good to have 2 physical devices separated and not in touch with each other. Borders, they provide external connectivity. Every time you reach outside your specific fabric or your fabric site, you go via the border. It can be a border with an IP handoff, where traffic is just encapsulated in IP via fixed or via VRF Lite, or you can have an SDXS transit that you just connect to another fabric site, and that we just maintain the entire fabric information. We have the edges, of course. You need to connect your endpoint somewhere. You're not building a network just to be able to connect control plane nodes and borders together. The edges is where you connect your endpoints, your cameras, your PCs, your wireless APs, your wireless clients, and everything. Yeah, you have a question?
How many borders can you deploy?
So the question is, how many borders can you deploy? I don't think we have a limitation on the number of borders. I think you can have a lot, but typically most customers have about 4 per fabric site. But I think you can grow pretty high because there's not really a limitation. for the number of borders because we just import the routes into the fabric, and then it just routes on an edge device. Is basically we just import one specific edge, and on a border we import a subnet. For the fabric, it doesn't matter. It's just a number at the end. So I don't think there's any number, but I have to double check it. But it can go quite high because there's really no limitation with that one. Control plane node is different because there every edge needs to build a session to the control plane node, but the border they can just import what they have. So fabric devices can have multiple roles as well. So you don't have to take a separate edge, a separate control plane node, a separate border. You can also combine them. Most people do the control plane node and the border node into one device. The control plane node is not that much functionality. It's all based upon software and receiving the Lisp traffic. The border node obviously does the hardware forwarding. So they combine really well. For very small sites, you also have the ability to use a fabric in a box. Then you're basically an edge and control plane node and the border at the same time. It's very convenient, especially for small sites. You just have like a 9400 there. You have a lot of line cards there, just connecting some endpoints. Even you can link it off to some other edges on that specific site. It's also the border, it's also the control plane node. And if you want to, we can also run the WLC there. So it's very convenient. You don't have to start adding additional devices on a small site just to be able to run SD access. You can put everything in there and still onboard that specific location into your SD access fabric, and then uplink it to your main site. So the way to look at it, it's a fabric, so physically you still have everything connected. You have your underlay network, can be intermediate nodes, can be Cisco Catalyst switches, can be anything, as long as it routes IP traffic, obviously runs the routing protocol that you use in your underlay network, and has an MTU that's bigger than 1500 bytes. We use encapsulation, so the normal 1500 byte frame needs to be encapsulated. So we typically use 9100 as an MTU, but if you have any devices that run up to 1600 byte MTU, they should be perfectly fine to be able to run SD access through it. It's all transparent because it's an overlay technology. With SD access, you can create a virtual network. On the normal network, we just create an overlay. You create another one, another one, another one, and we just create more overlays over the network. The underlay network is unaware of that. It's all tunneled between loopback and loopback. So even if you have 1,000 virtual networks on top of your underlay network, the underlay network will not be aware of it, which will also give you the benefit of your underlay network being more stable, easier to maintain. In traditional networking, you have your endpoints there, they leave, they need to move, they need to migrate, they come on, they go off. So the routing topology inside your underlay network would be more dynamic. With SD access, the underlay itself is just basically advertising all the loopbacks of the edge devices so that they communicate to each other. And that's all that you need to have there. So it's much more stable, and you will have less changes inside your network, which typically also makes it more stable. Everything above there is the virtual network, and it just gets being deployed dynamically by Cisco DNA Center. It just deploys it everywhere, and the only thing that you need to make sure is that you have the handoffs on the border nodes to be able to hand off the network somewhere else. So we use some key technologies in SD access. The first one is the Lisp protocol. It's the locator ID separation protocol. It's an old protocol that was already used in the internet. It wasn't very popular at the time. It's a tunneling protocol as well. It has its own encapsulation method, but it basically allows us to just tunnel the traffic to the network and look up remote destinations, similar like you would with DNS. With DNS, you just ask, like, what is this specific name? What is Cisco.com? You get an IP address back. With Lisp, we do it differently. We just go to the control plane node, and we just say, where is this specific IP address located? The control plane node tells us where it's located. We just tunnel the packet there, and that way we can create an overlay network. Cisco TrustSec, it's another technology that we use inside SDA. It's our segmentation. Every packet inside the fabric will put a tag on there, a CTS ingress tag, so that we can classify it throughout the network. With CTS, we enforce on egress, so every packet coming in gets tagged with a CTS tag, a group ID. On the egress side, we can just see, okay, this packet came from this specific group. There are the access lists there saying, okay, I want to allow this, yes or no. So it's just a matrix saying this specific group can talk to this specific group, yes, no, or if there's an access list combined to it, if they can talk, what exactly will we allow out? We'll also show that later in the slides as well. VXLAN is the encapsulation that we use. Lisp itself also has an encapsulation for pure IP packets. Because our SD access solution also allows layer 2, we're using VXLAN. With VXLAN, we can encapsulate the entire packet inside the VXLAN packet and tunnel it through the fabric. Obviously, we don't interoperate with VXLAN like EVPN, but we do use it internally. So just to look at Lisp overview, Lisp is a routing architecture. It's not just a routing protocol. If you have, for example, ERGP, RIP, OSPF, BGP, they just exchange routing tables. Lisp goes a bit deeper because it integrates directly into your routing architecture as well. Instead of just providing a RIP update saying, well, this specific route is there, Lisp goes further and goes into the Ceph tables and actually programs the route in Ceph saying, if you go there, you need to go there, which is different than you have with your traditional routing protocols. They just build your tables, they hand off the tables saying, well, here's the RIP, go form a FIP and see how the forwarding works. So it's much more integrated, which also for troubleshooting is a bit different. You don't just look at the Lisp tables to see where things are, you also need to look at Ceph to see what the eventual decision was that Lisp actually starts putting into it. We have two address spaces. We have the locators, which are the RLOCs. That's typically your loopback interfaces of all the devices. That's also what Cisco DNA Center pushes. Everything is being advertised with the loopback of the edge device or the border node. And you also try to reach the edge device and the border node. So all the traffic is tunneled between the loopback interfaces. It's a UDP protocol. We just forward traffic based upon that. As I said before, it's analogous to DNS. Instead of actually asking who is a specific host name, we just ask where is it located. Where is 192.168.1.1? Lisp will tell you back that one is specifically behind 10.1.1.1. You tunnel the traffic to 10.1.1.1, and then you can just de-encapsulate on the other side, and you reach there via the overlay networking. So it's a bit different, but it's also very flexible, and it allows us to build the SDA fabric in the way that we want, integrated as well with fabric-enabled wireless. It gives a lot of flexibility and allows you to do what we do with SDXS. So a lot of terminologies inside Lisp and SDXS that kind of match on the same thing that you might hear when you're troubleshooting things. On the device side, we have the ETR, the egress tunnel router, and the proxy ETR, which is the thing that's running on the border node, but it's also just an egress tunnel router. In SDXS, that's the edge device, the border node, and it connects the Lisp side to the Lisp-capable network. So it's basically taking the traffic, encapsulating it, sending it to the other side, also taking care of the registration and things like that. On the other side, we have the ITR. It's doing the opposite direction and also sending traffic from the network towards your edge devices. Most of our devices are XDRs. Basically, you get ingress traffic, you get egress traffic all at the same time, so we call them an XDR because it's performing both the same functions. It's registering everything with the fabric, but it's also looking up things on the other side. So all our devices are XDRs, but you could theoretically make them separately inside Lisp, but in SDXS, that's not really happening. We have a map resolver. That's the part of the control plane node. That is the component that actually responds to the map request. So whenever an ITR wants to forward the traffic, it just sends out a map request to the control plane node to be able to get a response back. That's the map resolver component of the control plane node. There's also the map server, and the map server just gets all the registration from all the fabric devices saying this specific endpoint ID is located behind this specific RLOC. The map server and the map resolver, obviously, you need to be on the same box because you cannot respond to a query if you don't know where it actually is. So they typically run on the same box, they commute together. And then you have the MSMR, the map server, map resolver, which is what we use in the SDXS connectivity. Endpoints, the endpoint IDs, that's the IP pools, your VLANs, your subnets, they're all endpoints. All your edge devices are part of the endpoint network. The RLOCs, the routing locators, that's the loopback IDs from the fabric devices. So every fabric device, especially if you use Lanimation to push it out, it has a loopback interface. And that's the RLOC we use for connectivity throughout the fabric. We send it from loopback to the loopback, and that's the connectivity you will have. It's also for troubleshooting. It's very convenient if you want to make sure that the path between two fabric devices is work. You can just do a ping towards the loopback of the other device. You take the source, loopback 0, and you can see if there's at least IP connectivity via ping between the edge devices. So to look at endpoint registration, obviously what the goal is to build on the control plane node is a table which contains all the information. You need the layer 2 information, you need the layer 3 information. You also need the ARP information on the control plane node because we sometimes want to do ARP rewrites. And also you need the subnets from the border nodes. So that's the table that the control plane node has. We have instances ID to be associated with specific networks. So if you have a layer 3 virtual network, it gets assigned a layer 3 instance ID. It typically starts with 4099, 4100, 4101, 4102, and so on. That distinguishes the network on the Lisp side. So the Lisp side will have an instance ID, and it corresponds to the VRFs that you will have on the edge devices or your border nodes. The control plane node just works with instance ID, so if you look on the control plane node, you will never be able to see the VRF name. The only thing that you will see there is the instance ID associating with it. We also have layer 2 instances because we do layer 2 SDA as well. There we don't have one per virtual network, but we have one per virtual pool, and it's associated to a VLAN. The VLAN is only locally significant, so on edge 1, that will be VLAN 1021 corresponds to VLAN ID 8189. Or to layer 2 Lisp instance ID 8189. That only stays there. The VLAN header is not being transferred from edge to edge. Only thing is done is being encapsulated with the layer 2 instance ID, goes to the other edge, he sees it's part of that specific VLAN, and if needed, he will create a VLAN header if it's going to a trunk, or just sends it out inside that VLAN. So the VLANs are locally significant only, but they are being linked together using the layer 2 instance ID that we carry inside the Lisp packets. Wireless endpoints, they work a bit differently. We're just covering the wired side in this specific training, how they work. With wireless, especially for layer 2 connectivity, the WLC obviously is responsible of who's located behind which access point. So instead of the edge devices learning the MAC addresses, the WLC will actually see the client authenticating to a specific access point, and it will use map notification messages from the WLC towards the border node to be signaled back to the edge devices saying, well, you learned a MAC address on your specific AP, so you have to add it. This training will only cover the wired side, but the wireless side, for most parts, works differently, works the same, but the only thing for registration, the wireless endpoints, they don't get learned, but they get signaled from the WLC side. Yes, question?
If there's more than one control plane active within the packet side, how does the registration then move on? Will the edge node register with every single control plane?
Yep. So the question is, if you have multiple control plane nodes, how does that work with the registration? So the way that it works, if you have 2 control plane nodes, we have 2 Lisp sessions to both control plane nodes. Every edge device will send the registration to A, and it will send it to B. Or if you have 8 control plane nodes, if you want to have really a lot of redundancy, it will send it to 8. Because they all work independently, they don't synchronize between each other, so they all need to know about the registrations to be able to fulfill the network. And if one crashes, the session goes down, but as soon as the session comes back up, the edge device sees that the Lisp session comes back up, and it will push back the registration, so that control plane node will just take itself out of production for some time to be able to relearn everything. And so before it actually starts responding again, it will make sure all the edge devices send the information back to the control plane node, and it becomes operational again. So they all work independently, and it's up to the fabric devices to make sure that they all know about what's going on. So this is how it typically works. So you have your network, you have your edge devices, you have a control plane node, a border node. Typically what first happens is that the internal borders, they come up, you register your IP subnets, your shared services subnet. It gets imported on the border node, or you can use epoxy ETR as well, but in a lot of cases we just import the routes. That gets being sent to the control plane node, it's getting registered. It's a /25. For Lisp, it doesn't matter if you register a /32, which is an endpoint, a /25 for a subnet, or if you register a /8 if you have a really big network. It just accepts it, it takes it, and puts it into the control plane information. Then the edges, they typically come up, clients boot up. We discover our layer 2 MAC addresses. They start using DHCP, static IP, that we snoop the ARPs from. That information get also learned by the edge devices. We register them up to the control plane node. The control plane node acknowledges it to us and saying, well, thank you, and he puts it in there as well. So at that point, when everybody came up, everybody's working, we got a nice little table. We have some layer 2 instances, 8189. The RLOC is edge 1. Obviously, that's just the name that I put in there. Typically, on the edge on the control plane node, will give you the RLOC IP address. We register either the MAC address, the IP address, or if you have, from the border, you just have a route being installed there. From the border nodes, you can use either imported routes, which just means that from a BGP session or something, you have to import your shared services subnet, your networking, or if it's something coming in. Or you can use the default border, and the default border is just your default access point out of the network. It's like a static route. If you don't know where things need to go, we'll go to the proxy ETR, and we go out of the network there. That's not being done on the control plane node on the borders. That's something that's running on the edges itself. Cisco DNA Center just configures that specific configuration, pushes it to the edge devices saying use PETR, and that's the IP addresses. That also changed with the coming of Lisp pub/sub. With Lisp pub/sub, we no longer use PETR, but there's a way to actually signal from the border nodes saying, I know the default route, and then it's being pushed out via pub/sub to all the edge devices saying, well, I know the border. That will be the default border, so that the 0.0.0 route is coming from me. That's more for SDA 2.0. With the legacy SDA, we use the PETR. But you will slowly see a change going from SDA 1.0 with just BGP configuration to pub/sub. With pub/sub, it just makes it more dynamically as well, where your dynamic border will be. You can also make it more dependent on where the default route is. With the current setup, if you use USPETR, it's a static route. So if that remote destination is not reachable, we'll still try to reach it and push traffic to it. Not always desirable, because it might not be able to accept it. It might not know the default route. And then SDA 2.0 with Lisp pub/sub and a dynamic default border will help, because there we only advertise the default route if it's actually reachable. So that's much more convenient. Currently, we have a lot of people running EEM scripts. If the default route on the border is down, they just shut down the loopback interface to be able to stop edges from actually pushing traffic there, thinking that they know where the default route is. So that's getting better with SDA 2.0. And of course, if you import all the routes, you don't have that problem either, because that's dynamically, if the route is imported, we'll use it. If it's actually removed, we'll stop using it. So virtual networks and Lisp instances, as I said, we have an entire fabric. Not everything uses the same methodology. On the Lisp side, we use instance IDs. On the fabric devices, we know about the Lisp instance ID, but all the forwarding is based upon VRFs, VLANs, and things like that. If you have the VRF on one side, you have your layer 3 instance on the fabric side. Together, that's called the virtual network, which is what Cisco DNA Center will push towards your edge device. If you look on the edge device here, mine show IPVRF Brew-esque, which is the one I typically use in my lab. I don't know why I picked that name. It's in Brussels. I'm part of Escalation, so I started using it once, and I keep on using it. Show IPVRF Brew-esque. You can see there we have a loopback 409 interface that's in the overlay network. That's typically used for multicasting. If you have multicasting, obviously for PIM sessions in the overlay, you need to have a loopback interface to be able to register with the RP. We'll push that one. It's just located on this edge. It's unique for every edge. VLAN 1021 is where your clients are located. We have a virtual interface, Lisp 1004099. That's the fabric interface. It's a virtual interface, but it's where we basically push out all the traffic and encapsulate it into instance ID 4099. And then you have VLAN 1022 as well, and Tunnel 2 interface, which is also for multicasting. That's part of the VRF that we can just push the updates to the rendezvous point. If you look at the configuration, you can see it configured there as well. You have parts of the configurations. You have router Lisp, instance ID 4099, that's the configuration for that one. We specify the dynamic EID, and the dynamic EID basically defines what the device can learn. So if you have a subnet that's located behind it on your SVI 172.30.30/24, just a subnet, or the corresponding IPv6 subnet, it's being configured as a dynamic EID. If there's any IP address on that specific segment coming on, like 5555 comes on in that specific subnet, it won't get registered with Lisp, because it says, well, my dynamic EID is this specific range. I'm only going to accept these specific IP addresses. Anything outside this specific range will not be accepted. It will just be ignored by Lisp. So especially if you start subnetting, I had some customers that started subnetting, and they messed up their subnetting so that their printer was just outside the subnet range. Everything worked except the printer. It would never register with Lisp just because it was outside their /27 that they were using in that specific subnet. So especially if you start subnetting, make sure that you are taking all the devices into subnet there. With Lisp, you can just create a very big layer 2 network with a lot of hosts in one specific VLAN. Because the way that we work with the fabric edge devices, it doesn't really matter if you just constrain them on one specific subnet or you make one specific IP range. We also have the static IP configuration. Under servers IPv4, we first link it with EID table command to the specific VRF on the specific edge device. And there you see the static database mapping 172.32.131/32. Then the locator set, and the locator set basically just tells Lisp, okay, use this specific locator set, and the locator set just refers to use loopback 0 as the IP address that I want to advertise onto the network. So if you have any hosts connected to a specific edge device that you think I want to have them in there, but they're not really part of my dynamic EID, or I just want to have them statically there, you can use the database mapping command, just copy over the locator set from what's already there, and then also start adding those there. There's also the map cache command. The map cache command is really important because if we don't have the map cache command there, we don't actually start looking up things. So we'll talk about that later, but you can see there map cache 000/0 map request. That means for every other host that we try to get into this instance ID that we want to reach, we will send out a map request to the server. But we'll cover that in the other part of the training. So we also have the SVI and the VLAN configuration. We use the IP anycast, so that means the same IP address is used on every edge device. If you have 100 edge devices, they all use the same configuration. Here, for example, show run interface VLAN 121. You can see we use a static MAC address, the VRF to link it to the virtual network, and the IP address. And this specific IP address will be used on edge 1, edge 2, edge 3, edge 4. No matter how many edge devices you deploy inside the fabric, they all use the same MAC address, they all use the same IP address. That's also why we don't want you to start trunking edge devices together. We use static MAC addresses. If you take one switch here, one switch there, you trunk them together, they both use the same MAC address. The intermediate switch will go crazy trying to relearn because the MAC address will just keep on flapping back and forth. So the configuration is the same everywhere. That will also help you because normally if you want to deploy it on a normal legacy network, you need an IP address per switch. Here you can just push 1,000 edge devices out. They all use the same IP addresses. It doesn't use up your pool with IP addresses. It just gives you one IP address for the default gateway, and that's being used, and the rest will use the same thing. So you always have to make sure that everything matches between edge devices, especially with some provisioning issues from Cisco DNA Center. The configuration might not match certain things. So if you have problems with specific locations, just check the configuration on that edge device. If you're not sure if it's this good or not good, just check the configuration on the other device. Make sure that it matches and everything is the same thing. Obviously, the underlay network will be different. Your loopback 0 and the underlay will be different and stuff like that. But the configuration for the interfaces on all the edge devices should match up in the same way. So it's a good thing just to verify if the configuration is pushed correctly, or if you have really a big problem and the push from DNA Center is not working, theoretically you could just take your configuration of one edge device, change the IP address, make sure you get the right key, link it up to the layer 3 network, and just manually put the configuration there. That works perfectly. It's not very user-friendly. It's not the way that you need to do it. But in some cases, when you have a provisioning issue, you need to deploy one specific fabric device, and Cisco DNA Center is giving you some errors. You could theoretically just take the configuration of the overlay network, push it onto the configuration of that edge device, and that way you can still bring it up while we try to figure out why Cisco DNA Center is having an error message itself. So that should work. I've done it with some customers, just be able to get them going again when their Cisco DNA Center didn't want to help them any further. So to look at the Lisp database, the Lisp database is very important inside the edge device. The Lisp database is basically a combination of all the statically configured IP addresses that you have via the database mapping, everything that we import via BGP or any routing protocols, all the dynamic EIDs, they all get put into the database, and that's the database that we use to register with the control plane node. So if you have any problems with the reachability towards a specific edge device, that's typically what you want to look at. You look at your Lisp instance ID, you give the Lisp instance ID that you want to use, either the number, or if you're lazy like me, you just take star, and then you get them from all IPv4 database. You can give a specific IP address, or you can just look at the entire table, and we'll just show you everything that this specific edge device has learned. In this case, it learned the dynamic IP address 172.33.3, dynamic EID, the locator set to the loopback 0 interface, priority weight, that's always going to be 1010 for edge devices, and the state is reachable. If it's down, that means the SVI is down or something's wrong with that specific interface. So it's a very important place to start looking at. If you have problems with endpoints that aren't reachable through the fabric, make sure it's actually inside the Lisp database on that edge device. Maybe it's not being learned. We have silent devices. If silent devices don't actually send something from time to time, we don't know about them, so they might disappear. But if they're not in the Lisp database, they won't be into the Lisp control plane node. And if they're not in the Lisp control plane node, nobody will be able to reach them. So it's always important to check that. And as I said, it's the combination of everything on that specific device for endpoints that need to be learned. Okay, question?
Is there any timeout in this endpoint?
So the question is there any... Yeah, so the question is there any timeout for the host to be learned? And that's mostly the MAC address table that will actually maintain that, the ARP table and things like that. Device tracking keeps track of when, where, what. And that's also a lot of problems with the edge devices that are silent. We have device tracking. Device tracking sends them ARP probes. They say, thank you for the ARP probe, and then I'm ignoring it. If they would just actually respond back to us, that would actually solve our problem. But the most problem with silent devices is that we learn about them, we try to keep them alive with ARP probes, and they just don't respond back to us, so then we age them out. If we age them out, we don't know where they are, and you're depending on either layer 2 flooding or something else to actually keep them alive. So that's typically the problem that we have. There are really only a few devices that really never send any traffic, and with one customer that never, if you plug in that device, it just doesn't send out anything. It only will send something when you actually start reaching to it. And they needed to do a migration, and that didn't quite work. They needed to just wake it up itself. Yeah, one question? Yeah, so the question is, what's the best practice for silent devices? Unfortunately, there's not really one approach that works with all the edge devices, with all the silent devices, because they all have different ways to wake them up. I've seen a lot of customers that have very good success, especially manufacturing environments, where they use the IP-directed broadcast feature. So they just have the IP-directed broadcast features enabled on their IoT VLAN where all these devices are. And they just send a broadcast ping to everything every 5 minutes or something from a small container that they put on the edge device. They just ping it all the time, and that keeps them alive. And that's, for them, what's the thing that works best. You can use static things, like you can start making device mappings and things like that. But unfortunately, all the devices are different, so the way that we actually have to work with them is also different, because we need to find a way to wake them up. And that's typically our problem. You know, we need to wake them up to make sure that they actually send something. And the broadcasting seemed to work a lot in that environment, at least, and that for them was a solution. And I've seen other customers use that as well. But some customers get creative. They just create a TCL script just to ping all the devices all the time and things like that. It's really per job. If there was one big solution, we could just deploy it by default, but there's no one solution for silent devices. We should get these IoT devices to realize that it's good to be silent, but you know, the network does want to hear to you from time to time. And but that's typically the IoT devices. They want to keep everything as minimal as possible, save power, conserve power, and don't do anything that they don't need to. But if they could at least ping the default gateway every few minutes, it'd be a lot easier for us. But we have to work with it the way that it is. Yeah, so the wildcard is very useful sometimes, especially if you want to dump everything. You just do show Lisp instance ID star, and you get everything from everything. So what we use inside Lisp is inside SDA is the reliable transport. The original Lisp implementation was using UDP. It just sent a notice towards the control plane node, go learn this. You never know if it actually was being learned or not. We use Lisp sessions, which basically means you build a TCP session towards your control plane node, and the control plane node will ACK everything back. There's a TCP session actually active between the edge devices and the control plane node, so by that TCP session being alive, you actually know there is reachability. If you see your sessions coming down, sometimes there's just nothing to register, so it's built upon the need. So if you have an edge device that just booted up, there's no clients, there's no multicasting, there's nothing actually needing to be registered, the session will be down. You have it a lot on borders as well. If you have a fabric in a box where you have a default border, there's basically nothing being learned from the border inside Lisp. So this Lisp session from the border towards the control plane node, which is just on the same device, but it still uses a session, will be showing down just because there's nothing to register. So that might not be a problem. But if there are devices, the Lisp session should come up. If it's not coming up, that might mean there's network connectivity. You need to just check TCP connectivity between the devices. So show IP TCP will help, just to see if you can actually reach the control plane node, yes or no. So if that's down, that's typically a big problem. We also had issues with the Lisp keys. In the original implementation of Cisco DNA Center, we used a very secure key called UCI. It was deployed everywhere. Everybody was using one key, and it was UCI. Security requirements, obviously, it's good to actually have a key that's not the same thing in all the networks across the entire globe. And now we have a new key that's dynamically generated per specific fabric site. The problem as well is, though, that you need to migrate from UCI to that specific key. You got this little banner on top of Cisco DNA Center saying we need to apply these security changes. You start pushing it, but then also unreliable devices, they couldn't be reached and things like that. And it became quite messy with some locations, especially during the migration side, because the registration just stopped, the WLC didn't accept it, and things like that. We had a lot of bugs in that specific area. You know, list session might come up, might not come up. The registration was just failing because there's a key mismatch between the edge device and the control plane node. The edge device just tries to register something. The control plane node says, well, it's nice, you're using a different key as I have. We're not actually going to allow that. There's also a lot of more things you can see with the show list session. I can show you in my lab just to see if it works right now. Hopefully that's also readable. Hopefully both of them will work today. Yep. So if you look at show list session on my specific device, here you can see, hopefully I got 2 list sessions from the specific edge device. I hope it's readable even in the back. Otherwise just wave, then I can make it even bigger, but then things start going off the screen. What you can see there, what I normally look at, you have the in, the out frames. That's very important. It needs to be active if something's happening. You know, if you have clients registering, deregistering, that should be changing. The number of users is also very important. Here I see 17 users. That doesn't mean I actually have 17 users connected to the edge device. That means I have 17 registrations that actually use that specific Lisp session. So if I look at the command show Lisp vref default session, and then specify one of the IP addresses, it will actually show you what those users are. And that's very useful, especially if there's specific issues with something going on. First, you see here, messages in, messages out, some error counters in case there's something going on there. But you also see the users that we talked about before. Here you have all the users coming in. You can also see per instance how many packets going in and out. If you have a Lisp key mismatch, you typically see only one user, and that's the policy subscription. The rest will never come up, especially if you have a WC in your network and the Lisp key is mismatching there. Well, list session is up, it's showing 1, but you only have 1 user connected. There's only 1 user connected, that means it's not doing anything. It's not doing any of the layer 2 instances, it's not doing any of the layer 3 instances. So always make sure if you look at the list session that you at least have more than 1. Because if it's only 1, that means it's not doing anything. There's no layer 2 instance associated with it, no layer 3 instance associated with it. This is a newer version, so you see all these subscribers as well for PubSub. It's also being added as a user. So it's very important to check that specific part of your list session. If you have any control plane registration issues, make sure that at least you have more than 1 user connected to it. And then if there's one specific instance having problem, for example, one of the VLANs is not working the way you expect it to work, you can distinguish here between the registrations per VLAN to see if it's registering everything. It's much easier than debugging it. You can also enable the debugs, but then if you enable the debugs, it might overload what you're looking at. So that's a very useful command. It's quite well hidden with the list session, with Lisp default to make sure that everything's there. Let's see if I can get it back. So that's a very useful command for troubleshooting, especially if Lisp key mismatches. The users will just be 1 and nothing will be there. Show TCP brief, make sure that the session is up and running. Also make sure that's stable. If it's just bouncing up and down, it might hint that there is any intermediate networking issues going on. We also have statistics, some map register statistics, map register messages going in and out per instance ID, so you can also use that to be able to see what's going on inside your network. We also have layer 2 endpoints. Obviously, we do layer 2 and layer 3 lists. Layer 2, we learn dynamically or statically IP addresses. The tricky part with layer 2 endpoints is if you run authentication, the MAC address is learned dynamically, but because as soon as it gets learned dynamically, we start an authentication session, an access session, It then becomes a static MAC address. So you will see there static for a specific port or dynamic. They're all being learned dynamically on the edge devices, and they will be registered with the control plane node. We won't register the SVI MAC address, as you can see there. It's got the bit set, do not register. Obviously, all the edge devices have the same MAC address. You don't want them all to register that specific MAC address. It will overload the control plane node. We did test that with one customer where we had a bug that bit was not set, and they had a few thousand edge devices with about 200 VLAN pools, IP pools on every device. They all started registering their MAC address with the control plane node. The control plane node did not like a few thousand packets per second registering that specific MAC address, and eventually the bugs crashed. We fixed that, so hopefully you won't see it there, but if you do see high CPU on your control plane node, it's always good to make sure that we do have the do not register bit set for your IP address, for your MAC address that's on the control plane, on the edge devices itself. Then you also see the normal MAC addresses that you learn. You learn them via dynamic, static, via authentication. We register them. Here you can see it just shows you it's on the box. The show Lisp database itself for Ethernet does not tell you where it's being learned. It just knows it's learned on a VLAN. So it's not a MAC address table. It just says it's on this box. Then it hands it over to layer 2 forwarding, and there you should be able to point to a specific interface. It's being learned dynamic EID. The dynamic EID range for layer 2 switching is just learn all the MAC addresses. There's nothing specific there. It's not a subnet, so we learn all the MAC addresses. We register with a control plane node, and from there it should be able to be reached. The SVI MAC addresses are excluded, and the MAC address, as I told before, for wireless, we do learn them, but we learn them via a different way. They get signaled from the control plane node to point to one specific access point that might be connected. And then in the MAC table, instead of actually seeing a port, you will see access tunnel 1, 2, 3, 4, 5, 6, up to how many access points you have. In the MAC address table, you also see CP learn. That's the remote MAC addresses that we actually learned. There's a map cache entry corresponding to that, and we'll cover that in the next section. But then you see CP learn, and the port will be layer 2, Lisp 0.8, whenever you might need to reach. So from the control plane node, you can look at the information as well. Obviously, you want to see what's being registered on the control plane node. It has a view of the entire network, so you can either use show Lisp site if your network is not too big, or if you want to have it a bit smaller, you can do show Lisp site instance ID and then get a list instance ID. You get a nice overview. It's up, yes or no. Some entries that are statically on the box, they will not be up and running. You see yes, and behind it you also see the hash mark. The hash mark is very important because it actually signals that we learn it via TCP reliable transport. If you have a Lisp key mismatch or some misconfigured device, you might see it as yes without the hash mark. That means it's not being registered via TCP. That must mean that it's something wrong with the registration of that specific one. So it's always good to check out why it's not being sent via reliable registration. Who last registered? That's the edge device that last registered it. There's no limitation that only one edge device can register, or even from border nodes, you can have a subnet being learned from 2 border nodes. They both import them. This will only tell you who's the last one to register. It doesn't tell you who everybody is. So if you're looking at this table and you think there might be something wrong, it might also just be the case, especially with subnets that you import from a border node, it might just be the case that another border node also registered and it's showing here. To be able to get the complete view of things, you can add the detail command and it becomes very big, or you can just specify it. Show list site, you give a specific IP address. In this case, I'm using a /32, but it could be your imported route. Instance ID 499, and then you get a complete overview. When it was first registered, when it was last registered. Proxy reply, that's something different that we do with SDA, where traditional Lisp, instead of actually the control plane node responding to a map request, with SDA, we configure the proxy bit so that the control plane node will respond directly. Instead of actually forwarding it to the egress tunnel route that actually registered it, the control plane node will just respond directly. And that's what the proxy bit says. It just says the control plane node is allowed to respond on behalf of the registering ETR. It does save a lot of bandwidth in the network. Instead of the control plane node just forwarding everything to the ETRs, it just responds back to it. So it's always important to make sure that that bit is set. Otherwise, you see a lot of extra traffic around your network. State complete, that means it's completely registered. There's also some registration failures. If you see them incrementing, you get to the Lisp instance ID mismatching, or the Lisp key mismatching. ETR information, in this case, there's only one ETR information showing. In the case where you have border nodes that are both registering a specific subnet, Here we just get multiple ETR informations. You see the priority, the weight. If they're the same priority and weight, they both will actually start load balancing between them. If there's a difference, it might take only one of the two paths. Status up is very important to also check if the remote destination has, for some reason, the SVI down or becomes unreachable. Status down, you can't reach it. So it is in the control plane node. He knows about it, but he also knows that it's not going to be used. There's also the TTL, the time to live. Any IP address or EID that gets registered, it has a time to live. So we need to re-register it every day to keep it into the table. If it's not being re-registered, it will be removed after what specific day. So that gives you a good overview of what really is there. And sometimes, especially with border nodes, it's good to look at here because you want to know both the ETR information and not just one of them. And then you see the locator, that's the IP address that actually will receive the traffic if somebody sends to it. So layer 2 control plane. Wait, that's the wrong title. So for registration history as well, sometimes it's good for a device, especially if it's roaming around the network, to see where it's being learned, where it's being removed, if it's moving around. It's not that much an issue for wired client, but sometimes it's just good to see what actually is going on inside the network. If you use the show list server registration history, here I'm just doing the last 10, but you can just make it as big as you want. You can actually see when actually something was added, when it was removed. If the client is having specific issues during a specific time and you're looking at it, well, it's there now, I don't know if it was not before. It's always good to look at the Lisp registration issue just to see if the device maybe have been deregistered and just came back. Because when you're troubleshooting, it's normally after the fact. So it might be during the fact that the customer actually complained, it was deregistered, then it came back, yes or no. But this is where you can actually find that. So it's a very useful command, especially if you had issues in the past. And the log is still there, so you can actually see if it was or it was not being deregistered on that specific edge device. So the layer 2 control plane, to make it easy, we put the layer 2 MAC addresses on a different location. Instead of on a show list site, we put them on a show Lisp instance ID, then the instance ID for layer 2 Ethernet server. Again, you can use the start command to get everything, or you can just use that specific command to get an entire table. Looks exactly the same thing as you had with IPv4, except in this case, it gives you a MAC address and gives you a layer 2 instance ID. Instead of it will actually tell you an IP address. Lisp doesn't care, it's just something that's coming in the register. If it's a MAC address, an IP address, it doesn't know, it doesn't care. It just registers and puts it there. The same thing for the registration history. For Ethernet, it's a lot more common to actually see roaming, especially if you have wireless roaming events going on. This command is very useful to see, was the client roaming, yes or no? Was it being registered by the WLC, yes or no? And things going on. So in the case of any roaming issues, this is a very useful command. You can see where the client has been, which AP, which location, who has been registering, and things like that. And was it from the WLC, yes, no? Was it a roam, yes, no? If it's a roam, it typically gets signaled by the WLC. So it's a very useful command, especially for wireless and roaming troubleshooting. Address resolution information. As I said in the beginning, we also have IP to MAC mapping. A lot of times these days we have layer 2 flooding. We can flood the ARP and get everywhere. You also have environments where layer 2 flooding is not enabled. If layer 2 flooding is not enabled, obviously the overlay is not broadcast capable. So we need some way to actually rewrite the destination MAC address and know where a specific IP address is. So if an edge device has a client, it's coming on, it's trying to ARP for an IP address on a different edge, device tracking will snoop that specific packet. It will say, well, this is an IP address. I don't know where it is. So where we do internally, we just ask Lisp saying, well, I've got IP address 1222. Do you know what the corresponding layer 2 MAC address is? If we know it inside the fabric, we will just rewrite the destination MAC address. Once we rewrite the destination MAC address, we can just tunnel to the remote location. Instead of a broadcast, it will become a unicast frame. Gets to the remote destination, gets to the client. He responds back because he doesn't care if it's a destination broadcast or a unicast. And they can ARP between each other. With layer 2 flooding enabled, basically we can flood the packet. But if you don't have layer 2 flooding, this is what we do. You also need to see the registration. So to be able to get the registration between an IP address and a MAC address, we use device tracking. Device tracking runs on the boxes. You see DHCP, NS, router advertisements. It sees everything going on. So it will contain mapping with show device tracking. Database. It will hand that information over to Lisp, and Lisp will register that. If you look here, show Lisp instance ID, Ethernet server, address resolution. you get an overview of all the IP addresses and all the MAC addresses that you have in your network, both for IPv4 and IPv6. We might not need to rewrite them all the time, but this does have a complete table. So sometimes if you don't know where a specific IP address is located, it's a good place to look at. Just look at the IP address, you get the mapping for the hardware MAC address, and then you can just look that up to see where it's being located. So reaching remote endpoints is also something obviously you want to do. You just don't want to register something, but you also want to get there. We have our table, what's where inside the fabric. So the first thing, endpoint 1 is starting to send a packet towards endpoint 2. It can be either a layer 2 packet, it can be a layer 3 packet. We just know it's going to a destination that we don't have a location locally. The CPU gets a copy of the packet. If it's an IP packet, we'll just forward it to the border for forwarding while we try to resolve it. If it's a layer 2 packet, we might flood it via layer 2 flooding or not, depending on if you have that configured. Edge 1 just initiates the map request to the control plane node saying, well, I got packets that are destined to this specific IP address. Do you know where it is? The control plane node can respond back saying, yes, I do, or no, I don't. If it doesn't, then we just have a negative map reply. It gets the information to the edge device. The edge device puts it into the map cache, and then the next packet that goes towards that destination, it doesn't need to be looked up. It will actually be forwarded to that destination correctly. Map cache does have a lifetime as well. Typically, it's 1 day for positive map cache entries and 15 minutes for negative map replies. So this is the way it works. So the packet, especially these days for IP packet, we just do packet loss forwarding. That means the first packet gets sent to the border for forwarding while we're trying to resolve it, and then the next packet will go directly. So the map cache, it's getting triggered as well by hitting actually a map cache map request entry. So for edge devices, you typically see the map cache 000/0 map request command. That means that we start configuring an entry inside Ceph saying, okay, if there's anything hitting this specific subnet, just send the packet towards the border node and send me a copy so that we can resolve it. External borders, obviously, if you have the proxy ETR, the USP ETR configured, they don't have that. You want to forward the IP traffic natively. You don't want to actually push traffic back to the list network, especially on the border side of things. So in a lot of cases, especially if you have multiple proxy ETR configuration or external border configurations, make sure that they don't have map cache 000 configured, because you want to just route via the FIP. You don't want to route back into your fabric on those specific locations. For edge devices, we just want to have everything pushed up to the control plane, to the border node. For border nodes, not so much. We cache them. By default, it's a TTL of 1 day. You can change that. There's a command, ETR map cache TTL command, that you can use on the registering devices. You can actually modify that 1 day to become less that. I only seen one customer do that. There was somebody who had a problem with a lot of small switches that were overloading the TCAM. They were all just students walking around the campus, so they said, well, they're never going to be here 1 day. They're just going to stick around for 1 hour and want everything to be cleared after 1 hour. They configured the ETR map cache TTL for 60 minutes, so the client just came on, just got removed again after 1 day. But you have to do it on the ingress registration, because the ingress registration will register the TTL with the control plane node, and that TTL will also be used to have the lifetime on the edge devices. Negative map request, if the control plane node doesn't know about something, it will also tell you that it has a TTL of 15 minutes. After 15 minutes, we just keep on trying. Did anything change, yes or no? And that we keep it in like there. The control plane node also doesn't just tell you it doesn't know about that specific IP address. There's some blocking mechanism going in there. If you ask for one specific IP address, it will tell you, I don't know what it is, and it belongs to this specific block of IP addresses that I don't know about it. So a lot of times you start looking at SDA, especially when you first deploy it, and you see in your Ceph tables on the edge devices some subnet that you don't have in your network. They're typically associated with negative map requests. If you have 0.00/1, that means I don't know the entire bottom range of this subnet, and it just puts it in there. It's a dynamically generated thing, and it's just to protect the CPU, especially if somebody's pinging 1.1.1 all the way down to 1.25.1.1.1. Instead of just looking everyone up separately, the control plane node just says, I don't know this entire block. It will input some strange blocks inside your network that you might not recognize, but it typically come from the map cache entry, and it's typically from the negative map reply. So if you do see them, that's typically where they come from. There are also actions that we can take, especially on the border nodes. We want to just forward traffic natively if it's not inside the network. But on edge devices, we want to forward native, and there it just means use the use PETR configuration if it's present. If you don't know where the route is, push it towards the proxy ETR to be able to get out of the fabric, because that will be the default gateway. On borders, obviously, when they have a normal IP route, that's not going to be needed. So to look at the map cache, there's the command show Lisp instance ID, and then you give the instance ID IPv4 map cache. Here on the top, you see my 000/0 route encapsulating to proxy ETR. You also see their static send map request, so it's not combined just by sending to the proxy ETR. We're also sending a packet to the control plane node to resolve it. For the other one below there, you see the 000/1. That's one of the subnet that just my control plane node told me, like, I don't know this entire block of networking. So it's half the internet, basically, that it tells us, I don't know about this. Forward native, encapsulating to proxy ETR. There's no static send map request there. We know we're not going to be able to resolve it. Don't bother sending another static map request entry for me for the next 15 minutes. I don't know this entire block. So it just says, well, go to the proxy ETR for traffic if you need to go that way. Don't ask me. The uptime is 11 minutes, 29 seconds. After that time, he will try again just to see if anything changed. If nothing changed, he will just keep on saying, well, I don't know this block of IP addresses. No need to resolve it. And it's just to protect the CPU from being overloaded if somebody starts doing a ping sweep to the entire range. Obviously, we don't only have negative entries, we also have positive entries. That's what you see there on the bottom. Via map reply, we got the complete entry. That specific IP address I can reach via that specific locator. The state is up. You can just start reaching it. If you want to encapsulate any traffic, you want to take that one. That's what you typically want to see. The problem with layer 3 destinations as well is you have to be careful if you look at it on an edge device. We do layer 2 and layer 3 forwarding. If you start working inside an IP pool, like 3.2 is talking to 3.4, 3.5, 3.6, it's going to be forwarded via layer 2. So it might not show up in your layer 3 map cache, but it will show up in your layer 2 map cache. So if you're looking at the layer 2 map cache, make sure it's actually outside the specific IP pool, because we only trigger a lookup if it's outside of the IP pool itself. Inside, we'll just forward based upon layer 2. Obviously, then we don't trigger a lookup for the layer 3 environment. So it's very useful to look at, especially just to see what's going on inside your network. For layer 2, we do the same thing, but we don't have a proxy ETR. We either do layer 2 flooding just to flood to the multicast group, or we just drop the packet if we can't find the destination and it's not local. Remote destinations, if you look at the show macOS dynamic table, you will see them being learned CP learned. That means we learn it remotely via the control plane node. Layer 2 Lisp is the egress interface. And then you can see it in the Lisp Ethernet map cache. It's also associated with the VLAN. The layer 3 interface is associated with the VRF. This is layer 2 VLAN 1021. Associated with Lisp instance ID 8189. So that means this specific packet, if the client is talking directly between each other inside the IP pool, even if it's IP packets, it's just being layer 2 switched from macOS to macOS, and it's going to that specific locator. Uptime is 1 week. That means it's just been active. These two clients, they have a ping connected to each other, so the uptime is 1 week. Typically, in normal environments, you don't have a lot of east-west traffic. Most traffic will be to your data center, to the internet. But sometimes, like IP phones, cameras, and things like that, they will talk to each other, and then it's good to start looking at the Ethernet map cache. 90% of the troubleshooting that we need to do is mostly just endpoints reaching the data center, reaching the internet, reaching their whatever they need to reach, and it's based upon layer 3. But if you have IP phones or devices that talk to each other, you need to start looking at layer 2. But in 90% of the cases, all the traffic goes to the border, goes out to the internet, and the clients, they don't talk to each other. Especially in enterprise environments, there's little point-to-point connectivity going on. So most of the troubleshooting that you will do is looking at the layer 3 instance, but it's always good to remember there's also layer 2 going on, especially for the case for IP phones and things like that. So to look at traffic forwarding, as I said, you have your normal packet that you want to transmit through the network. We encapsulate it fully inside VXLAN. So we build a complete new Ethernet header, IP header. UDP we take as a 5689, I think, is the UDP port. There's a specific VXLAN header that we populate with information. And then we encapsulate the entire packet. If you start looking at packet captures, you will see for layer 2, you will see the entire packet. For layer 3, obviously, we add a layer 2 header, but it's just a dummy header because with layer 3 forwarding, the layer 2 header doesn't matter. It will be present, but it will not contain any useful information just because it's going to be a routed frame. For layer 2 frames, obviously that's going to be different. The layer 2 header should be intact and will be transported across the network. We also put the SCT tag in there. That's for our secure fabric part of the network. Every packet going to the fabric will be tagged with an SCT, regardless if it's known or unknown. Even if it's unknown, we typically just put 0 there, which is just the unknown, which is also a valid SCT tag. Every packet will be tagged. Every packet will be enforced. If there's no policy, obviously it will always be allowed, but we still do that. So to look at that from a capture perspective, this is the capture I took from the lab from 2 devices connecting. Here you have your layer 2 encapsulated packet, the destination, the source, the complete packet is there. It's an IP packet. It's an ICMP, obviously it's a ping. We have a new header, a new destination, macOS. You see the packets going from source port 65472, which is a dynamically allocated port, towards 4789. The destination port will always be that VXLAN UDP destination port. The source port will vary, and we need to vary that because you also want to do load balancing through your network. If we would use 4789 to 4789, if there's any intermediate devices there that want to load balance your IP packet, it will always see the same packet. It will always take the same path. By alternating the source port, we actually start load balancing inside your network. So there's some hashing function. Every packet will take its own unique path and will not be load balanced. But if you have multiple streams going on, they might take a different path. And that's mostly based upon the source port that will be alternating. That allows those intermediate devices to do load balancing actually more effective. Then you have your VXLAN header. You see your layer 2 Lisp instance ID in there. In this case, it's a 8189. It's a layer 2 frame. And we have the group policy ID 4. This one is using authentication. This specific packet was assigned to a specific group ID, and it was actually tagged with group ID 4. We don't use the names inside the packet, obviously, because that will be kind of more complex. We just take the ID. We send it to the other side. He will receive it saying SCT ID 4 coming in. You want to go out to where? And then it will say it's allowed, yes or no. So that's how we transport packets, especially on the capture side. You can use EPC on the 9K as well to receive those packets. You have to take careful that we do the packet before the rewrite. So layer 2 header for the old packet, for the new packet might not always match. But if you do it on the receive side, you will typically see the packet coming in and you will see exactly what's going on, and you can also use that for troubleshooting, which can be quite useful. So packet forwarding, as I said, it's an overlay technology. Packet comes in, we have the map cache information, hopefully. We just encapsulate it into VXLAN, send it over the other device from loopback 0 to loopback 0. The other packet gets it, he knows it's a packet, needs to de-encapsulate it. He strips out the new header, takes the new information, looks what port needs to go out, and sends it out to the other side. One thing that's important is reachability. We're only going to send packets if we actually deem the destination reachable. We had a few variations on the reachability. We had minimum max length 32. That means that the device will only forward it if it has the /32 of the other device in its routing table. We had exclude default. That means we'll forward it any way you want, as long as it's not using the default route. We have minimum max length 24 on some locations. So it's always good to make sure that in the underlay network, at least you have full reachability between all devices. All the loopback zeros are advertised as /32. If you start summarizing inside the network, you have to make sure that you have the right configuration there. If you start summarizing everything into a /24, that's fine, but also make sure that you have your minimum max length from 32 set to 24, plus you might actually start blackholing traffic, because we send traffic towards the destination, we expect it to be reached. If we send it to a /32 on the other side, we know it's reachable because it's advertising itself. If it's doing it to a summarized network, we just know that the subnet where he's located might be reachable. We don't know if it's actually reachable or not. So that's the risk of summarization. You can change it to /24 if you want to have less routes. But then this edge device does not know on the other side if it's reachable or not. He will just send traffic to it. He thinks on the other side somebody's receiving it. He won't know if it actually gets there or not. There are some probing going on, but that's typically slower than just looking at the RIP saying, well, that edge device went offline. It's removed from the routing table. If it's removed from the routing table, I can't reach it. I don't have to send packet to it. So that's very useful, but it's also very important to make sure that you check the reachability, especially if you have problems forwarding, make sure that the routing table in the underlay network knows about everything. So we have layer 2 and layer 3 forwarding. Sometimes it's very obvious. A lot of clients, as I said, most of the traffic is going northbound, it's going to the border, it's going out to the internet, to your data center. Everything goes up north. You only do layer 3 forwarding. Like IP phones, though, cameras, IoT devices, they do use layer 2 forwarding. And in that case, you need to start looking at the layer 2 forwarding itself. Inside the IP pool, we typically only send traffic via layer 2 instances. So IP phones on a subnet connected, they talk MAC to MAC. If we know about the SVI MAC address, we'll forward it via layer 3. If not, we'll just flood it or not flood it, depending on what the configuration you have. So on layer 3, we forward based upon the destination IP address. On layer 2, obviously, we base on the layer 2 MAC address. You can have layer 2 borders, you can have layer 3 borders, so there's always a possibility to extend the network, the layer 2 border handoff towards your legacy network, or you have your layer 3 handoff going to the internet, or what you have. If you look at the routing table, that's what typically people look a lot, especially if you come from a legacy environment. You do show IP routes, you do it on your edge device, you think something's broken because there's nothing there. There's no default gateway, there's no routes. This device can't reach anything, which is the first thing you will see, especially if you're used to normal troubleshooting. You don't see it, but it will be on the border. The border node will say null routes. Obviously, that's also a problem if you come from a legacy background saying, well, I see a null route, that means the traffic is being black-holed. To really see the things within things, you have to use Ceph. As I said, Lisp is a routing architecture, it's not a routing protocol. With a normal routing protocol, you would see the things with show IP route. With Lisp, you will see everything in show IP Ceph. You can see show IP Ceph even for the route that was not there in the routing table. There you can see the detail. You can see everything's going on the IP Ceph layer. Lisp programs it directly into Ceph. It doesn't go via the routing table. It just goes directly to Ceph saying this specific location is reachable via this specific thing. So if you start troubleshooting, always get the show IP Ceph information. You have a few keywords, you have detail, but you also have internal, gives you even more information. But it will tell you how exactly the forwarding goes on within a network. This is a command that we use most of the time for troubleshooting, especially forwarding issues with layer 3. You get the show IP Ceph output, you get on the edge device, you get it on the border node. Not even if you look at what Lisp is saying, typically we just first look at what Ceph is saying, because Ceph is basically telling us what's really going on the forwarding plane. And then we can see where things are going. If it's pointing to the right direction, we don't even have to look at Lisp. If it's not pointing at the right direction, we need to backtrack into Lisp to see why Lisp might be telling us something different than we're trying to do. So show IP Ceph is very useful when you have forwarding issue. Always check and make sure that you also add the detail or internal keywords just to be able to see what's really going on. Because that will really tell you the picture of what Lisp decided to do with the packet and how packets are forwarding. A lot of the times, if there's traffic being black-holed, Ceph is just pointing to the destination that you don't want to expect. It's pointing back to the border node. It's expecting somewhere else. It's pointing traffic to the CPU or what you have. So it's a very important command. And for every different subnet, you will see what's going on there. For layer 2 forwarding, obviously you don't have to look at the Ceph table for layer 2 forwarding. You look at the MAC address tables, or you can look at the show platform hardware fat switch MATM table command. Not a lot of people use that for troubleshooting, but if you want to look at it, this is the command. This is the hardware side of things. It's on the FAT layer, which is the platform-dependent layer on the Catalyst 9000. There you see one specific entry that I highlighted in blue. You can see the type. The type within the MAC address table means what type it is. In this case, it's been tagged with 0x1 and a lot of zeros. And a dynamic address, that means it's a Lisp that remote address is being dynamically learned. You can also see the port where it's going out. It's going out that specific RLOC, and then you have adjacency information, which is more for the platform side to troubleshoot. So it's a very good way to look at the layer 2 MAC address table if you want to see where everything is forwarding on layer 2, because typically if you look at the show MAC address table, it will just tell you it's going to layer 2 list. But if you use this command, you will see the corresponding RLOC. Obviously, you can also look at the database information, but the database information is just what it's going to say. And this is from the forwarding plane saying, well, packets are going to get rewritten to that specific destination. Layer 2 flooding is something that's also broken a lot that people don't even know about. We only use it for flooding broadcast, unknown multicast. A lot of the traffic goes northbound. People don't talk back and forth. We just flood ARPs, but then again, nobody actually notices it because, except for IP phones, nobody actually talks from PC to PC. They have a broadcast on the lane network. if you don't have it set up correctly, we only push it towards an underlay group, but we don't actually verify if that underlay group is operational. If you have an RP, if everything is working the way it's supposed to be working, we just configure it, we push traffic to it, and we expect it to get to the other side. A lot of environments, especially when they were pushed in the beginning, something changed, the multicasting underlay isn't working the way it's supposed to be working. Then people start using layer 2 flooding. It's broken, they don't understand why. It's just because the multicasting group never worked. It's just not the way it's supposed to be working. We do flood bump traffic, so broadcast, unknown, unicast, and multicast packets. With multicast packets, we only flood the layer 2 flooded multicast packets. We don't just go flood every multicast packet. There are some variations inside SDA that we flood multicast packets with TTL1, but it also depends which software version you have. So if you need to flood traffic with TTL1, we can do that via the broadcast underlay, but make sure that you run at least the latest version, because in an earlier version it was broken, and even TTL1 packets that were multicasting inside the subnet, we tried to route them. Obviously, if you try to route a TTL1 multicast packet, you're not going to go very far, and the packet was being dropped. So if you do have that type of traffic, we can flood it, but make sure that you have a later version. Flood ARP and ND for IPv6, and flood unknown unicast is also configured on a specific instance ID to make sure that we flood that traffic. If that's not there, we don't flood the traffic, we just absorb it and either drop it or try to rewrite it. So this is just to look at something, show IP and route for that specific group. The first one is showing the loopback 0 of my specific IP address, saying, okay, I'm coming from this specific loopback 0. If I got clients there, I expect, especially with these days, every PC sends some traffic out that's broadcast, flooded, or something. PCs are quite chatty these days, so if there are clients connected, I'm typically a source in that specific group. So a good thing, what I normally check is, do I see myself as a source in that specific group? That means there's something actively sending. But also, do I see all the other edge devices? Because they also should be sending, and because I'm part of the group, I also joined the group, so everything is coming back to me. So it's a very simple check. You do show IPM route for the group. Do you see yourself? Do you see everybody else? If you don't see everybody else, if you're missing one location, either he's not sending any traffic, or something is broken with his multicast configuration. On your own side, you just see the outgoing interface being the interface that you're sending the traffic to. On the ingress side, the outgoing interfaces will be varying layer 2 instances. So if it's one working, one is not working, make sure that it's added to the outgoing interface list. All of them should be listed there, otherwise we don't de-encapsulate the traffic from that specific location. So it's very good to check, especially if you have layer 2 flooding that you want to work, but it's not working the way you expect it to work. And surprisingly, a lot of customers aren't aware of that. They just expect everything to work because nobody reported it broken, and then you start looking at it and it's missing RP configuration or something like that. So the secure fabric, that's the next thing that we're going to look at. That's the authentication side of things. A lot of the things, we have software-defined access, and obviously software-defined access, you want to have everything dynamically done. But doing that, we use .1x, a map, so clients, endpoints, they connect to the network. They authenticate via ICE, and ICE will tell the fabric what to do with that. And that basically makes the entire fabric dynamic. It makes it that you don't have to go into the port assignment and just do all the assignments yourself. We can send a lot of information, voice domain authorizations. If you have IP pools, you want to go into the voice domain. You don't want to go into the data domain. VLAN assignment, you want to assign the client to a specific IP pool, depending on how he classified, what group he authenticated with the AD, or what kind of MAC address, if it's being profiled as a camera, things like that. SGT assignment, you want to make sure that it gets assigned to specific SGT to make sure that the traffic actually is being classified. Dynamic access list, if they're still being used. We don't see them much because we tend to use a lot of SGT and SGC ACLs. But you can still use the DACLs if you say, well, I want to limit this specific client to one specific thing, as we do for legacy. We can still do that. Templates, sometimes used with, especially with access points, when they get classified, we push an access point template to it saying this is your VLAN and things like that. We can push a lot of information. We even have MACsec downlink customers where you actually just get the should secure information being pushed down from ICE. The switches themselves, they just run the authentication and they just depend on ICE to actually say what's going on. When you start troubleshooting, it's important to note though that on Catalyst 9000, all the authentication is done by the SMD process. When you normally log into the iOS switch the Catalyst 9000, you end up in the IOSD daemon. It's not running the authentication natively. If you do show commands like show access session, you will still see everything. If you want to debug it and you start enabling debug.1x or debug radius, you won't see anything. You will see if somebody SSHs into your device because that's taken care of by IOSD. But for the authentication side, there's also radius going on, but it's taken care of by the SMD process. So the SMD process in the back gets all the traffic tunneled. If it's radius traffic, which is interesting for SMD, it's not being absorbed by IOSD, it's just pushed towards SMD. SMD takes care of it. It also sends the packets to the radius server through IOSD. So it won't actually show up with debug radius and debug.1x. If you want to enable the traces, all the debugs that you normally were using with .1x, they are available. But you have to enable them via set platform software trace, SMD, session manager, switch, active, R0, then the facility that you want to do. If you do a question mark there, you will see all the things that you saw before, radius for both, things like that. .1x packets, EPM, everything that you used to have is going to be there. You specify a level that you want to enable on. It's always on tracing, so it's always logging some information, but the default level is notice, so it's not going to be that much information. But you can, for example, enable tracing for radius. You just set that to a verbose level, and you start seeing the packets going back and forth. To gather the traces afterwards, you have to use the command show logging process SMD. I'll show you that on the next slide. First, we'll look at the show AAA server status. There you can also see IOSD has a state for the radius server. In this case, it's up. The platform state for SMD is also currently up. We had some cases in the past that they weren't quite in sync. IOSD was saying up, SMD was saying down. If it's down, it's obviously not going to try authentication and going to do things like that. So you have to always check the show AAA server, making sure that both of them are reporting up and up. If not, you need to find out why it might be responding that. They also have their own dead timer showing you total dead time and how often they count. Typically, they should match quite well, but they're not always in sync. This is the traces that we enabled. As you can see, show logging process SMD, include radius. This is your standard radius, debug radius output, but then in a specific format that is just cutting from the show logging process. The normal information, you have the calling station ID, port ID, username, sent to the client, to the iServer. The iServer is responding back saying, this is an access accept. Tunnel type VLAN. There I have my tunnel private group ID, which is the VLAN that the client is going to be assigned to. My SGT tag, C801, the SGT name, CL client 1, and the VN that we belong to. So that's the information coming back to the ICE. The client is then authenticated, put into that specific VLAN. And if you do show access session for that specific interface with details, you can see there's the client. This is an IP address that's being learned via device tracking. The status is authorized. That means you got an access accept. If it's unauthorized, we get an accept reject. Domain is the data domain. It's not a voice client. Every traffic will be sent untagged. This is the policy that we use. And then you get the server policies. VLAN 121, SGT tag 200, and a .1x is authentication success. That's just the method success. It doesn't mean it actually got authorized onto the network. It's just saying, I run the method went OK. If it's failing, that doesn't mean that the response that came back was failing. It just means it didn't actually get a packet from the client to initiate .1x. It falls over to map, and then map will run after that. Now to look at Cisco TrustSec, the thing with Cisco TrustSec that you have to take into account is that we do egress enforcing. All the packets coming into the devices itself are enforced on the egress side. So we carry the packet throughout the network. On the egress destination, we take a look at saying, is that destination allowed, yes or no? So the packet does travel to it. With typical firewall people, they like to drop the packet as quickly as possible. For us, we want to carry it to the network. When you actually leave the CTS domain, we see, OK, is this traffic allowed, yes or no? If we don't allow it, we just drop it. There's a default action applied, so there's a matrix with everything between them, yes or no. If we don't have one matrix that's actually being filled in, we hit the default action, and the default action is going to be either drop, permit, or what will you have. You have to be careful when you start using the default action deny. It's the whitelisting module, which is very much secure, but also you have to make sure that you have all the permutations of all the devices, because if you got one permutation, it's just going to drop the traffic. Or what you sometimes have, when the device comes up and it downloads the default deny everything before it actually gets all the information, it can't reach this ICE anymore because it's also saying, well, this ICE actually is not allowed to reach my network, so I'm just dropping the packets itself. So if you start doing whitelisting, be careful to make sure that you always ensure that the traffic from your ICE server to your edge device is secured. Sometimes it's good to put a static mapping in there just to say this traffic is allowed, just in case that the default action gets downloaded from ICE before anything else. As you can see, this is the tag. We looked at it earlier as well. It's in the packet capture. Every packet will actually get that information included. So to look at a normal topology here, we have two clients talking to each other at different SGTs, also to the data center. On the data center behind the border, you have to make sure that you also download the information. By default, the border doesn't actually authenticate anything, so it doesn't dynamically learn something. You have to use either SXP to be able to download everything from ICE so that the border node knows who's what, or you have to use CLIs, which is nice for a lab environment, but it doesn't always scale that well. So a lot of times the border, it has an SXP session, or you can extend the CTS via CTS link to also enforce it on the border, and also on the ingress side, the border needs to place the right tag into the packet to be able to enforce it on the egress side. So here we have a small matrix that we created. From 200 to 300, we're permitting SSH, we're denying everything else. From 200 to 300, it's a different type of server, we're permitting HTTPS. We're not allowing SSH, we just deny everything else. So it's a unidirectional thingy, so this is being enforced one way. There's no bidirectional coming back, so if you actually send traffic there, it will be enforced, some of it, or to that one. Between those two, we have a deny all. All the traffic sent between those hosts will be dropped on that specific edge device. But with this specific table, the traffic from that server to this specific SGT, that's not matching anything in the table. It will hit the permit all. Because it's a permit all, the traffic will be sent. So it's very unidirectional, so you have to make sure that you do deploy it correctly, but also make sure that you understand traffic is only enforced one way. If you want to have a bidirectional, you have to make sure that you also have a corresponding mapping from 301 back to 200 to be able to also enforce it on that side. So it's very important for a security thing. Make sure that you don't expect, it's not a stateful thingy. It is actually going to do only one directional, and it's a stateless firewall thingy. Yes. The question was, is it only for unicast traffic? And yes, at the moment, we only have enforcement for unicast traffic. Multicast traffic is always going to come through. But we're looking into that for the next versions to also enforce multicasting. Obviously, you don't want multicasting just to flood, because that would open up some things. So that will be coming in the next version. So CTS environment data, it's very important that this can be downloaded from the ICE server. It's typically a very good thing to look at if you have any specific issues inside your network. Show CTS environment data. If it's not being downloaded, it typically means there's a connectivity issue. One important thing that it downloads as well is the device SGT. When it boots up the device SGT, which is the traffic actually being sent by this specific device, will be 0. It can download a varying number from ICE. In this case, it downloaded saying, well, all traffic towards the CPU, and from the CPU will be tagged with SGT tag 2. So it gets downloaded. You can see which server we actually start using for that specific one. It also references the pack ID, very important for SGT communication, making sure that everything is being downloaded correctly. You have your table being downloaded, which shows you with the show CTS environment data, all the varying groups that you defined on ICE or Cisco DNA Center, depending on which one has control of the network. It's a number matching to a name, and it's being downloaded. You typically see the number, and then you see -00, that's the version number. If there's a new name, for example, tag 200 will become CL client 3, it will be 200 -1. That's just the versioning behind it, but the first part is actually the number itself. Yeah, one question?
Is this data coming from the PAN or from the PSN?
Good question. If it's coming from the PAN or the PSN, I have no idea, because I'm the SDA guy. I just know it comes from ICE. So I'm not particularly sure. I think it's from the PX Grid persona, but I'm not even sure. So yeah, I'll have to check with one of the ICE guys, because I can just guess, which doesn't really help you much. So the CTS table is being downloaded. Also, the server table is being downloaded. There's a specific AAA entry saying CTS list. So we actually try to download it from a specific ICE server, and that one will actually tell us which are the servers that actually are being downloaded. We do refresh the information by default every 24 hours. If there's any change on the network, if you want to modify your security postures, obviously you don't want to wait 24 hours. If you press deploy on Cisco DNA Center on an ICE, it will just send a COA, change of authorization, towards the edge devices. The edge devices will get the notification. Something changed, they go to ICE and say, okay, what changed? And it downloads the new tables. So very important to look at the CTS environment. If it's failing, it typically is the pack that's failing. It's being refreshed very often. We had some issues as well that the CTS pack was not getting refreshed. So by the time it expired, it didn't get refreshed. So the edge device is using one pack, ICE is using another one. They don't really talk to each other at that time. That's a bug that's been fixed recently as well, I think in 17.6.4. So if you have CTS refresh issues, just make sure to get the latest version. If the pack is not there, what I typically look at is the credential lifetime. It's also being displayed on ICE. If it matches, that means they're in sync. If it doesn't match, that means one of the two devices is having a specific issue. So it's very important to have the pack. If you don't have it, nothing with CTS will actually be working. The mapping is also very important. We have every IP address at the moment is being linked to a specific SGT tag. We don't link it to the MAC address, we link it to the IP address. So everything is authenticated via the IP address, and you can see the show CTS role-based SGT map to get that specific mapping. And that means this IP address is being learned with this specific SGT tag. Layer 2 enforcement is also coming, but at the moment we only use it on layer 3, so all the traffic is being enforced. Even if you send it from layer 2 to layer 2, it still has an IP address obviously in that frame. And if it's an IP frame, we can tag it with an SGT tag. Local means it's being learned via authentication. CLI means that I was lazy, I didn't set up an SXP session, I just configured it on the border node itself. It's very important to always check the border nodes, making sure that they also have the SXP tables, because a lot of traffic is coming from the border nodes. So if you want to have a proper security posture, everything goes typically from the edge devices towards the border node. So make sure that the SGT tables on the border node have the right information. We need to tag the packet on the egress side, but we also need to enforce it going out. Can be SXP, can be CLI. SXP will be a lot more flexible, and I think with a newer version of SXP, you don't even have to get SXP per VRF. But that's a new ICE feature, a new iOS feature that's coming. It's already released, but it's not used that much. I think it's SXP 8 or something. So that will help that you have one SXP session for the entire VRF. At the moment, with standard configuration, you have one SXP session per VRF. Authorization entry is very important, because every time we actually learn about a specific SGT group, we will start looking at that specific group, and only then we will start requesting it. If there's no specific client actually in a specific group, we won't ask for the information. We only ask for it as soon as we learn about a specific group. In this case, we know about group 200. There's a client there. We'll ask ICE, give me the information regarding SGT tag 200. I have something I want to enforce, and he starts downloading it. Even if there's no response coming back saying, oh, I don't know anything about SGT 200, just use the default action. It's still important that the edge device actually asks for it and make sure that it's actually being downloaded. If you don't hit anything, we'll just do the default action, which is what you might or might not want. So it's very important to check that it actually asks ICE for information. So CTS role-based permissions, obviously it's good to download, but you also want to see what's going on. You can see the show CTS role-based permissions. In this case, from group 200 to group 300, allow web. If you look at the allow web information, which shows CTS role-based ACL, allow web. The allow web ACL will show you it's permitting traffic towards 80, 443, both TCP, UDP, and denying everything else, which is the policy that we looked at earlier. We want to allow HTTP traffic and HTTPS traffic. The rest, we just want to have being dropped. So it's being applied to the border nodes. Obviously, that's also the way that the traffic is. The specific host was on your data center. It was an HTTP server, so we're sending traffic towards port 80, 4043, and the destination port will be checked, and that's going to be the one that's being checked on the border node from the client. If you put this specific RBACL on the client side, obviously it's not going to be effective, because there the dynamic port will be the destination port, and the source port will be 80 or 443, and we won't actually start matching it. So it's very important to apply the RBACLs in the location that you want to apply them, and also to understand the destination where you are applying them to make sure that you have it. Otherwise, we'll just apply the ***, and everything will be there. Monitoring SCT traffic, there's a command show CTS role-based counters. It will actually tell you for the entire matrix what it is no. Is it accepting traffic? Is it denying traffic? And things like that. It's per ASIC, or per box even, so it's not going to give you a very good view per port, but it will tell you for the entire switch how many packets are being hit, how many are being denied, how many are being permitted. And if there's anything missing there, it's also a sign that we just didn't download it, there's nothing there, or we had failures downloading it. So it's a very good location to check if you have forwarding issues with CTS that's being dropped. Do we actually know about it in the matrix, yes or no? If it's not there, it's not being enforced. And you can look at it on both sides to make sure that you have the traffic. Hardware denied for software-based traffic, and hardware permit. Here's some useful debugs to be able to do debug CTS all, debug RBM all for the role-based manager all. CTS does run on IOSD, so there you can do debug radius, and it will actually show you the CTS stuff, but not the pack information. So you have to sometimes balance between them to be able to get everything. So multicasting, we'll have to skip this for now because we run out of time. My timing is very good, but especially for the guys that are used to our software releases, we're always late, so the same thing with the presentation. It takes us much too long to actually get them. For the multicasting, there is a good session as well for that Jaroslav is giving for demulticasting SDXS. But unfortunately, at the moment, we can't do that because we ran out of time. Sorry for that, but I need to talk faster sometimes, or less content. So thank you very much, and hope you have a good trip back.